So, we all want a world powered by clean energy, right? Solar panels, wind turbines, the whole deal. But there's this one huge, fundamental problem we have to crack. Let's get into it.
Yeah, exactly. What do you do when the sun goes down or the wind just stops blowing? That is the billion-dollar question, isn't it? How do we keep the lights on all the time? And look, this isn't some tiny little issue. This is the next great engineering challenge for building a truly reliable clean energy grid.
And this really gets to the heart of it. Our entire clean energy future, it all hangs on this one massive challenge. We've got to find a way to store all that power for days, weeks, maybe even entire seasons. And the solution? Well, it's got a name: long-duration energy storage.
Okay, so I know what you're probably thinking. Hold on, we have batteries, right? And you're not wrong, we do. But the kind of storage we need for the grid, it's a completely different beast. We have to think way beyond the lithium-ion batteries that are in your phone or your car.
So here's what we're talking about officially. Long-duration energy storage, or LDES for short. This isn't about giving your phone a quick charge. These are systems built to discharge power for 10 hours or more, sometimes way more. Their whole job is to keep the grid stable when the sun and wind take a break.
And I absolutely love this analogy. It just makes so much sense. Think of a normal lithium-ion battery like a sprinter. It's fantastic for a short, powerful burst of energy, for handling quick little adjustments on the grid. But LDES? That's your marathon runner. It's built for the long haul, for endurance, just steadily pumping out power for hours and hours and hours.
And the scale of this marathon, it's just staggering. I mean, just to get a reliable, renewable grid up and running, the US alone might need something like 460 gigawatts of this stuff. That is a truly mind-boggling amount of storage capacity.
And of course, when you have an engineering challenge that huge, a massive economic opportunity is right there with it. We are talking about a potential $330 billion investment opportunity. And that's just in the United States.
And this isn't some sci-fi, far-off future thing. This is happening right now. The market is absolutely exploding, growing at a rate of over 13% a year. This is it. This is the technology that is going to define the next decade of the energy transition.
So the big question is, how do we actually build these marathon runners for the grid? Well, it turns out there's not just one single answer. It's more like we have this whole toolbox filled with really fascinating technologies. So let's open it up and explore the 4 main ways we can store power for the long haul.
All right, first up, we've got mechanical storage. And the idea here is it's so beautifully simple. You basically use extra electricity to move something really heavy. The classic example is pumped storage hydro. When you have cheap extra power, you use it to pump a ton of water up a hill into a reservoir. Now, all that water sitting up there is just stored potential energy. And when you need the power back, you just let the water flow back down through a turbine, and boom, you've got electricity. It's literally using gravity as a giant rechargeable battery.
Okay, next up is electrochemical storage. Now, this is where we get into some really clever, advanced batteries that are designed specifically for the grid. A perfect example is something called a flow battery. So instead of having everything packed into a single solid box, like your phone battery, these things use these huge tanks of special liquids, electrolytes. To charge it up, you pump the liquids through a central stack where a chemical reaction stores the energy. To get the power back out, you just reverse the flow. And here's the brilliant part. You can scale up the power and the duration independently. Need more power? Build a bigger stack. Need it to last longer? Just get bigger tanks. It's incredibly flexible. Our third tool is thermal storage. And this one is it's genius. The basic idea is you take all that cheap renewable electricity and you turn it into pure heat. I'm talking about using that power to heat up a material like a giant vat of molten salt or a huge block of graphite to unbelievably high temperatures. We're talking hundreds or even thousands of degrees. And that heat can be stored for hours, even days. Then, when you need the power, you use that intense heat to boil water, create steam, and spin a turbine, just like in a regular old power plant. It's basically a planetary-scale thermos.
And finally, number 4, chemical storage. Now, this is where we get into the really long-term stuff. We're talking seasonal storage. The big idea here is using renewable electricity to run a process called electrolysis. It basically splits water into its 2 parts, oxygen and hydrogen. That hydrogen gas, which we call green hydrogen, can then be stored, like in huge underground salt caverns, for weeks or even months at a time. This is how you bottle the sunshine from July and use it to heat your home in the dead of winter. You just turn that hydrogen back into electricity whenever you need it most.
Okay, so that's our toolbox. We've got 4 completely different approaches, so which one's the best? Well, the real answer is it totally depends on what you need it for. They each have their own strengths and weaknesses, so let's put them side by side and see how they might fit together to create a complete solution.
And what's so cool here is how you can see the trade-offs, right? Mechanical storage, like pumped hydro, is super efficient, and it's a proven technology, but you can only build it in certain places. Electrochemical is amazingly flexible, but getting the right materials can be a challenge. Thermal can pack a ton of energy into a small space, and chemical, well, that's the absolute king of long, seasonal storage, but it's not quite as efficient at getting the power back out. So you see, there's no single silver bullet here. The real answer is we're probably going to need all of them.
And listen, this isn't just stuff that exists in a lab or on a whiteboard. These things are real. On the left, you've got the Ludington pumped hydro plant up in Michigan. That thing is a mechanical giant, and it's been working for decades. And then on the right, you have something totally new, Form Energy's iron-air battery. It's a cutting-edge electrochemical system that can provide power for 100 hours straight. So you're seeing the whole spectrum here, from the proven workhorses to the brand-new innovators, all being deployed right now.
So, what does this all add up to for the future? Well, it means the path to a 100% renewable grid is starting to look a whole lot clearer. And it's all being made possible by this incredible wave of innovation in energy storage.
And you know what else? The numbers are just getting better and better every year. Just look at this chart. It shows a really clear trend. The costs to build these systems are projected to drop a lot by 2030. So as those costs come down and the tech gets even better, the dream of a 100% clean grid starts to look very, very real.
So what's the big takeaway from all this? It's that we have the tools. We actually have them. From giant gravity-powered water batteries to making fuel out of thin air, the technologies we need to solve the biggest challenge of renewable energy, they exist right now, and they're getting better and cheaper every single day. The whole conversation is changing. It's really not a question of if we can build a 100% renewable grid anymore. The real question is how quickly and how smartly we can pick the right tools for the job to get it done.